Hello and welcome to our SCADE language introduction video. In this video, I'm going to explain the context of embedded safety critical application development, what a synchronous language is, and what the SCADE language specificities are regarding this topic, and then provide more details about its environment. First of all, let's explain what an embedded system is and what its applications are. An embedded system is a computer system designed to perform one or few dedicated functions, often used with real-time computing constraints. It is embedded as part of a complete device, often including hardware and mechanical parts. It is controlled by a dedicated real-time application software that is developed specifically for the embedded system. Some of these systems are safety critical. A failure may lead to a catastrophe. To give you some examples, they are embedded in aircraft, trains, used in the energy, nuclear, and transportation industries, and in many other consumer, medical, commercial, and military devices. How does it work? The embedded system interacts permanently with its environment, reading data and receiving events, producing actions to control this environment. The environment can be a process to control, a user, or a mix of both. The embedded systems are real-time applications. A real-time application can be interactive. This means that it interacts with its environment at its own rate. But a real-time application is very often designed as a reactive application that follows the rhythm imposed by its environment. This defines the notion of cycle, external to the reactive application. Many industrial real-time applications are reactive. Control, supervision, and signal processing applications are part of this category. The determinism makes the difference. The outputs of a reactive application are only determined by its inputs and their occurrences. The synchronous approach is a deterministic reactive approach. As I already said, the outputs are only determined by the inputs and their occurrences, and the synchronous approach is deterministic. This states that there is no delay between inputs reception and outputs production, and this greatly simplifies the design of the application. There cannot be overlapping of data between cycles. In practice, this means that each output is produced before the reception of the next input. In other words, the reaction time must be smaller than the delay between two input events to fulfill the synchronous approach paradigm. Thus, internal processing time can be considered as having zero delay. A synchronous approach comes with rigorous design methods and enables formal verification. This is very important because, as I mentioned before, errors in reactive applications can have dramatic consequences involving human lives and huge costs. And special care must be taken while developing a safety-critical application. This means no infinite loops, no recursion, safe memory management, etc. To ease the development of such applications, one must take into account these constraints. The SCADE language belongs to the synchronous languages family. It is the result of 30 years of research and development. It has been specifically designed to fulfill the safety-critical application development constraints by focusing on the needs of such applications in terms of data and control flows. In particular, it does not contain constructs that are potentially unsafe, such as unbounded loops or dynamic memory allocation. It has been used to develop numerous applications in civil and defense aerospace, transportation, nuclear, space, and automotive industries. The SCADE language is formally defined. There is no ambiguity when interpreting a model defined in SCADE. It provides an easy understanding between stakeholders, such as designers, reviewers, and testers. And it allows formal verification. The SCADE language is strongly typed. The types are Boolean, integer, real, enumerations, structures, and arrays. And the typing discipline can be checked by tools. The SCADE language offers a unique mix of data flow and control flow constructs, including state machines. The SCADE language is a deterministic and declarative data flow language. Thus, the order of equations does not matter, only the data dependencies. An equation defines an infinite sequence of values called a flow. A flow has a unique definition. It is comparable to a mathematical definition, where variables in equations have only one definition. The memory keeps track of the flow values from the previous cycle. Following the table, A plus B is the flow defined as the sum of A and B. The memory is illustrated here by the pre-operator that returns the flow of the previous value of the flows passed as a parameter. Obviously, its first output is undefined. A SCADE model is a network of operators. The arrows denote the flows of data between the operators that continuously compute their outputs from the inputs. The boxes are operations and flows. An operator is either a primitive, a SCADE model, or imported code, for example, external C code. A SCADE model is composed of a network of primitive operators, such as plus, and, or user-defined operators drawn as boxes. Operators may be purely combinatorial, or may have memory, like a counter or an integrator. All operators compute in parallel. Independent operators are not ordered, and the operators only communicate through the flows. The SCADE language supports array data type and iterators. Iterators apply an operator over arrays, for vector calculus or for replication. This optimizes the design while preserving the safety, thanks to the use of bonded loops. The top design is a flattened scalar product, and the bottom design is the same one, but using replication through iterators. The design is thus clearer and more maintainable. The SCADE language offers hierarchical state machines that can be fully mixed with the data flow behavior. Here you can see how a state machine works. You have a first state connected to a second one via a transition. The transition is triggered when its condition is true. The result is the interaction for the second state. Finally, dedicated constructs can be used for a fine-grained activation of operators, in order to control final code efficiency. Parallelism is expressed functionally at model level, without the task handling complexity. As a result, operating systems, which usually manage the task concurrence of an application, are less loaded. The computation order is based on the functional dependencies. Every data element is computed at the right time, once and only once. The generated code is efficient and deterministic and fulfills embedded code constraints, such as bonded loops or no-go-to. The SCADE Suite Integrated Development Environment is a model-based environment dedicated to the SCADE language. Its editor fully supports the SCADE language, as it recognizes each language construct and its proper use. Within the SCADE Suite IDE, or Integrated Development Environment, the user can edit and check SCADE models, perform traceability with requirements, perform model-based simulation and formal verification, perform model and code coverage, and stack and time analysis. And finally, he can generate code that will be embedded into the final system. The SCADE Suite generator, KCG, ensures that the input model is correct with respect to the SCADE language semantics. It generates C or ADA code that fits safety-critical applications constraints. It is deterministic. An input model always produces the same generated code with the same KCG options. The SCADE Suite code generator, KCG, is qualified and certified for the following standards: the DO 178B and C for the civilian avionics, the EN 50128 for the railway industry, the IEC 61508 for the industry, and is compliant with the IEC 6880 for the nuclear, and the ISO 26262 for the automotive industries. So this product is qualified at the highest level of safety across 5 market segments by 10 safety authorities worldwide. As a summary, SCADE is a language dedicated to safety-critical embedded application development. It has a graphical notation with formally defined semantics that really mix data flow and control flow constructs. The SCADE language is supported by the SCADE Suite model-based environment, and the embeddable code can be produced thanks to the qualified and certified code generator, KCG. Thank you for your attention.